because according to our rules, we cannot allow everyone to use your laptop to search anything. So if you already have your laptop with some page on the internet or any website, please turn it off. Otherwise, we expect you cheating someone. Okay? And as far as we know, we already know some group already use the internet to do the search. So please turn off your website. Okay? We cannot allow to do it again. Okay? Any question? Okay. Now, then we move on to our stage, third stage. And we already have our assignments for the problem number 4. Okay, so every group, please sign your names on the board. Okay, and now we move to the first stage for the reporter to prepare in 5 minutes.
有，看他刚才都不知道要用，我都跑到前面去死了。哦，提醒他们一下，他们的 point 啊，他们不是有 point 吗？
对。就看他们心情啊，他们应该是知道啊。
没有注意到，
就是荧光笔啊，不是荧光笔，就是他们说直接上去吃，有什么差？
哦，可以啊，提醒他们一下。
可以啊。可以跟他们讲一下。
跟report
就都可以啊，就都跟他们讲啊。
他们有那个吗？
他们应该有。没有，我没有。哦，老师，是没有的啊？是没有的。
没
有给他们。
是啊。那就
you can go ahead.
Honorable judges and worthy opponents, this is D1 reporting problem 4 shooting rubber band. So, the problem statement states that a rubber band may fly a longer distance if it's non-uniformly stretched and giving it a spin. So, the problem statement tells us to optimize the distance, and we'll be focusing on the relevant parameters and maximizing the distance. So, for the phenomenon, once it's unevenly stretched, it will create two strings. One string is thicker, which has a smaller elasticity, and then one is thinner and has greater elasticity. So, as you can see, this is how we do this unevenly stretched. So, creates a thicker string and a thinner string. So, for the phenomenon, through the unevenly stretched rubber band, the integration of the change of elasticity causes its kinetic energy to increase. While the rubber band restored to its original length, the unevenly stretched strings generates a torque that creates an angular momentum to the rubber band's flying motion. So the rubber band's volume remains the same throughout the stretching process. So we can derive equation 1, which stresses this condition of the constant of the volume. And through some manipulation, we get to equation 2. So we can then apply Young's modulus equation and plug equation 2 into equation 3. So we can get to this elasticity equation 3. So deriving the force by applying times distance, we can get to this restoration force, focusing on a single string of a rubber band. So in order to find the change of energy when launching the rubber band, we need to integrate the force while changing the stretching length, and we can get to equation 5. So we first consider a normally stretched rubber band that is without any unevenly stretched. We can get to equation 6 that we need to times this 2 in order to simulate the whole rubber band. So this is the velocity you can get due to this transfer of energy. So then, as the problem statement stated, we then consider about this unevenly stretched rubber band. And the change of energy will be as equation 8 shows. And the velocity will be equation 9, which is a lot bigger than the velocity that we derive from normally stretched. And if you plug in this delta x into 0, we can get back to the equation above describing the normally stretched. Then we're going to talk about the spinning. After it restores to its original length, with the restoration torque after the rubber band, we can derive equation 10. So in order to find its angular momentum throughout the flying process, we can integrate its dc type, and we can get its rotational energy and derive this angular momentum through that rotational energy. Then, after we finding this initial velocity, because the problem statement tells us to investigate the distance, we need to consider this air resistance during the flying process. So, through solving this air resistance differential equation, we can get to equation 14, describing the time of its flying. And our experiment, we're focusing on the rubber band, launching without zero angle but at a certain height. So by solving the x direction of differential equation, our final distance will be equation as shown in equation 15. So every time the rubber band launches, this airflow can cause it to have a deviation of attack of angle. And as there's an attack of angle in the rubber band, the air resistance will be distributed into a lift and a drag. And as this picture shows, the center of pressure act will be a little bit different from the mass center of gravity. Therefore, these two forces will create a torque and cause this unstable motion of rubber band flying throughout the process. And this vibration motion can cause energy to lose. Therefore, as we derive those angular momentum in the earlier pages, through the precession motion of this rubber band, we can get that the conclusion that this angular momentum created by unevenly stretched rubber band can decrease this loss of vibrational energy due to the torque act on this rubber band. So this is our experience setup that we put the launcher into a certain height without any angle. So to investigate this or optimize this distance of rubber band, we have to first establish this boundary. We have to first establish how this rubber band stretched throughout this its launching process, because its K value isn't a constant. However, it varies through the distance it stretched. So as the formula we derived, we can prove that this restoration force actually proven that this restoration force conforms with our theory. So as we calculate the energy that's stored when the rubber band is restoring to its original length. However, we all know that when the rubber band is stretching, it will cause some heat loss during the process. So in order to investigate this heat loss during the stretching process, we investigate the damping motion of the rubber band string. And as you can see, we simulate this damping motion and find out that this coefficient of damping is really small. Therefore, we consider this heat energy loss to be negligible. So then we establish a boundary condition in order to find this optimization of rubber band, this shooting rubber band. And throughout the experiment, we find out that the maximum length before the rubber band reaches its elasticity limits will be 26 centimeters. So next I will get into the parameters we've been discussing. First will be the elongation length and unevenly stretched length, torsion, and spinning. So first, we're talking about this elongation and stretch. And the elongation length refers to the original length that it stretches, and the stretch length refers to the evenly stretched length it stretched. So as you can see, as the stretch length increase, this distance will increase. And this is a theoretical model that we derived through the former calculation. And this part is the theoretical trend line where this part exceeds the elasticity limits, so should not be considered in our experiment. And as shown, as this elongation length increase, there's a general increased trend of distance compared to the last graph. So, and this 19.5 centimeters also has the same trend as the former one. And so this 21.5% of elongation that it increases through the stretching length. So in order to maximize this distance, we need to plug in the boundary condition, which we all know that the elongation length plus the stretching length should be below this boundary condition that we established in the former preliminary experiment. So we plug in the equation, substitute the equation, and we can get to this graph, which we found out this stretch in approximately 1.2 will be the maximum initial velocity or energy transfer we can reach. And this result will be 16.487 meters. So then we establish another factor that might affect this phenomenon, which is torsion. Due to, at first, we predict that this torsion can actually cause the vibration to happen, therefore loss of energy will occur. However, after experiment, we find out, and we think that due to precession, torsion decreases the loss of energy instead of increase it, which the experiment supports our prediction, and which this decrease of loss of energy will be approximately 4.78% based on the experimental results. So then we discuss about the spinning effects throughout the rubber band. So, and if we first look at the problem statement, we will think that this increase of distance is mainly focused on the additional spinning that's added on this rubber band. However, after doing the experiment, we found out this increase of distance is not really, spinning is not the main factor that causes this extension of distance to occur. And as shown in this graph, we find sets of that has the same initial velocity, however, has a sets that have angular momentum and without angular momentum on it. And which shows in this graph that the results show that the spinning actually has really small impact on this flying process, which we can predict it's because of the small surface area that the air resistance can act on this rubber. So then, if it's spinning in a vertical way, we can expect that the Magnus effect can actually produce a lift that may optimize distance. So, but after doing the experiment, we find out this Magnus effect of lifting forces is actually pretty small, and it's also due to this contact area, surface area of rubber. So next, I would like to establish some possible deviation throughout our experiment. That we all know this Young's modulus can actually be deviated throughout the deviation of temperature. But it's really hard to control the temperature of the rubber band throughout the process. Therefore, this could be a possible deviation in our experiment. So for the future research, as we shown in our experiment, we found out this change of airflow due to spinning doesn't really affect our distance a lot. However, we consider this effect is still worth to analyze how this spinning object with a little surface area can affect the airflow around it. And this is our conclusion that the velocity and the distance. And this is my report. Thank you, everyone.
Okay. So move on. So questions for yes.
So how do you measure your data? I mean the distance. How do you measure it?
In our experience setting, I stated that we first stabilize the launcher in a certain height and launch it without
So have you considered different heights of release?
different heights of release.
Will that change your experimental results?
Of course, because you've got more distance for you to actually.
Or will it change the trend or the conclusions of the experimental results?
No.
Okay. So have you ever measured the angular velocity of the rubber band?
We've tried to measure this angular velocity of this rubber band. However, it's spinning too fast, so it's actually not able to capture this spinning motion.
So the problem statement has talked about giving it a spin. So you think that spinning isn't the main factor of this phenomenon? Is that right?
I think the potential energy is the main factor that launches the longer distance, but we also acknowledge that spinning still has some effects on this phenomenon.
And how will it spin? If you have done your experiment in the video, how will it spin?
The spinning direction will be from this thinner string to a thicker string.
Okay, so in your theory, where is the center of mass of the rubber band? Because when you're considering forces, you need to have a center of mass.
Center of mass
Of the rubber band. Because the rubber band moves in, let's say, a wave-like motion. And how will you calculate the center of mass? It will change throughout the time.
I don't think that's relevant parameters throughout our whole statement.
Because what your theory has tried to prove the relevant parameters of analysis, and you need the center of mass.
Okay, time's up. The opponent has 2 minutes to check.
reporting on problem number 4, shooting rubber band. Okay, here's the problem statement. I think the most important part of the problem statement is the spin of the rubber band and the non-uniformly stretched. Although the reporter has talked about the non-uniformly stretched, however, the reporter didn't consider much about the spinning of the rubber band and the angular velocity that the band might reach. Okay, this is the outline. First they have the phenomenon, which is observed. And they did lots and lots of theory and made an experiment to try to prove their theory correct. Their theoretical model consists of Young's modulus, the change of energy while the uniformly stretched, torque, air resistance, heat loss, and damping motion. And they did an experiment with force versus the elongation length to try to prove their Young's modulus. And did an experiment on the distance of the rubber band. Well, what distance the rubber band will reach with an uneven stretch. And their theory graphs matches with their experiment. So the report has many strengths, like the consideration of many theories. The measures the distance of the shooting rubber band, and their correlation between theory and experimental results. And they found the maximum distance, which I remember correctly is like 60 meters. But they have the lack of consideration of rubber band spinning, the angular velocity, the rotation energy, which I think is an important part stated in the problem statement. And the difference of rubber bands, meaning that when they do the experiment too long, the rubber band might increase in elasticity. Okay, thank you. We can begin our discussion. Okay, so I want you to explain your data, because I can't quite understand.
Which data?
I mean the data of the distance, the shooting distance. I think this is the strange length and this is the education.
This is distance.
I think if you can make a graph, you can make the words bigger, right? Because we cannot.
Oh yeah, I understand. That's the same.
So what do you think caused the error bar during the experiment?
So as I mentioned during this, can you change the vibration part? Every time it launches, the rubber band has a different attack of angle, and this attack of angle deviates this vibration motion that can cause the loss of energy. And you just mentioned that we didn't consider the angular velocity. However, we did consider angular velocity, but by plotting in this angular momentum that it can act on this rubber band in order to decrease this precession motion and the lack of loss of energy due to precession vibration.
Well, have you ever calculated the rotational energy? So what percentage of the energy is rotation energy in your experiment?
What do you mean about the percentage energy?
Yes, because when you stretch a rubber band, there is a potential energy, right?
Yes.
And when it's unevenly stretched, I believe that you said that the potential energy will be bigger. Is that correct?
Yes.
So when you release the rubber band, some of the potential energy will be converted to rotational energy. And have you, because you said that the spinning can be neglected, is that correct?
The spinning can be no, that's not what I
Well, I
said.
thought you said that the spinning can be neglected.
What I meant is actually compared to the potential energy, spinning is a minor factor of increasing
Well, how
distance.
many percent of energy converts?
So in our calculation, we first established a linear kinetic energy throughout the stretching process. And the way we calculated this rotational energy is actually not related to elongation length, however, the unevenly stretched part. So the first
you
part,
have the angular velocity, and how can you calculate your rotational energy?
I have a
And
torque.
how can you just assume that rotational energy doesn't really matter?
I didn't assume, I used experiment to prove my data. And as you can see, we calculated torque during our process, and by integrating it with angle, we can get to our rotational energy. And I don't understand that which part is.
So you deduct other factors to leave the rotational energy out.
Can you rephrase the question?
So how do you calculate the rotational energy?
So can you show the torque?
Can you use the backward, please?
Sure.
Do you use energy or momentum?
So as the rubber band is stretching this is the original elongation length. So as the rubber band stretches to restore to its original length, the thickness and the thinner part still exist, and this
It's a conservation of volume, is that correct?
You mentioned
Thickness. Yes.
yes, exactly.
So you consider thickness for the cross-section area. Cross-section area of the.
Yeah, exactly. And this will cause this torque act on this rubber band and cause it to spin.
Okay. So you can, through this, you can calculate the theoretical angular velocity.
Angular velocity, angular momentum, and rotational energy. Correct.
You can calculate that, and you assume that this will be correct.
Yes.
Okay. So you assume from this, you assume that there is no energy loss.
As you can see, we did a damping motion in order to establish the heat loss during the stretching process. So there will be some energy loss during the stretching process.
Except for damping motion, I think there are other possibilities that energy might be lost, like how the wave, when the rubber band shoots out, and we can see a wave forming in the rubber band. Is there some energy converted to the wave?
Wait.
Yes.
I think you mentioned a very good point. However, in our experiment, we didn't observe this kind of loss of energy.
Experimental video. Well, if you put it in slow motion, you can see that there is a wave formed in the rubber band.
That's what you meant. Can you change to the vibration part? We consider this waveform is actually a part of vibration that we can reduce this energy loss through the increase of angular momentum throughout the process.
Well, how? Because
So we consider this fluctuation as a precession motion, that as the angular momentum,
I'm talking about the wave, not the precession motion.
so the wave is actually similar to the vibration that we are trying to express throughout
Well,
this.
do you think it is the same?
Well, I don't know how to define this wave, but in my perspective, I think that's what you're talking about.
Have you considered when you shoot out the rubber band, will the rubber band function like a frisbee? When you consider everything.
So it's like exactly shows in that picture that it will has a type of angle which causes it to transform this air resistance into a drag and a lift. So exerting the angular momentum on the spinning rubber band can decrease this unstable motion of this rubber band.
So in this video, in this photo or the schematic diagram here, you assume that the rubber band is a ring. Is that correct?
Yes.
Okay, so when the rubber band is like launched, it actually deforms and has a wave forming around the rubber band. So can we still assume that it is a ring or not?
The deformation you express is just the first part of the rubber band launching. After it launched to a little distance, it will become
There's still
circular motion.
a wave forming inside of the rubber band, and it actually. Can I use that for? Well, the rubber band might go something like this, and this will turn. Right? And you cannot really assume that it is a ring. And without any proof, with using slow motion to observe it, I don't know how your theory can apply in this situation.
So I think that the deformation you're talking is only fits in when the rubber band launches for a smaller distance. So after it launches,
So when you calculate your external results, you ignore the smaller distance that is launched. Is that correct?
So you're saying that this wave-like function of deformation of rubber band can cause an energy loss during the process, am I correct?
So it can actually conserve energy, but also cause energy loss since the kinetic energy is diverted.
Okay, so I agree.
So this might be a possibility of derivation of your
Exactly.
Okay. So can we turn to your experimental results when you predict the maximum? Okay, so the stretch length here is, what do you say, 1.2.
Maybe that's a mistake.
So how much? Daniel can speak out.
0.16
And there will be a maximum distance.
Yes.
So
This page is expressing, plugging in this boundary condition of 26 centimeters of stretch consistent of elongation lengths in the stretch length before the strain of rubber band exceeds its elasticity limits.
So you have no count of the elasticity limits. Is that
Sorry?
So you,
I mean, that graph is based on the boundary condition of the limits of elasticity.
so when it doesn't apply, when elasticity doesn't apply to the theory, you get more.
I'm sorry, can you rephrase your question?
So when it is out of the elasticity's boundary condition,
Yeah, I understand the question. So the problem statement states us, told us to optimize the distance. So once it exceeds its elasticity limits, rubber band will not be able to restore to its original length, and this will not optimize the distance, which is not conforms with the problem statement.
okay. So when you're trying to measure your uneven stretching, what kind of units are you using?
Centimeters.
Centimeters. So can you define a ratio of uneven stretching?
You mean the unevenly stretched length compared to the elongation length?
Yes.
Yes.
So can I ask more about the theory?
Sure.
Okay, so can we turn to the page where we talk about E-plus? Okay, so can you explain what the original data and the fitting curve means? How do you get the data?
So this is the part that we're trying to find this heat loss by
Yes.
Conducting a preliminary experiment of hanging a string and see how its harmonic motion or damping motion decrease the energy throughout the process in order to find this damping constant that's in this motion.
So is this experimental data or?
Yes, this is experimental data.
And how do you measure the experimental data here?
So what do you mean?
How do you measure the experimental? How do you do what's done?
So I've shown the damping motion and plug it into tracker and plot the y-axis in time plot and fit.
Do you have an experimental setup for this? Okay. Can you draw your experimental setup?
So there's a hanger here that hangs string that there was a bit of weight here.
Will the amount of weight affect the experimental results?
So we're trying to find this damping coefficient of damping of motion. So I don't think the amount of weight will affect the weight. So we're pulling a certain distance and let it go. So observe this vertical motion of this damping motion.
Okay. So this graph is one of your experimental results.
This is preliminary.
So have you done other experiments other than that, more mass or more different restrictions?
Since we believe that this mass doesn't affect the damping coefficient that's occurring in this
So you
phenomenon.
only do one experiment and just assume that the
No, we
damping
plotted
is
in
the same as the
plotted
equilibrium damping.
many times, multiple times the experiment, but we didn't conduct the different mass that you just stated.
Well, because you cannot assume that.
Okay, time's up. So Paula, please come back, give a summary.
Okay, so we talked a lot about your experiment and how your experiment is conducted. And we also talked a lot about your theory and how they calculated the rotational energy, the angular velocity, and the rotational momentum. However, I think that the reporters should conduct an experiment on testing the angular velocity with tracker to measure it and make it correct, to prove that the theory is correct. And we talked about how where the maximum distance will happen. We talked about how maybe an elongation ratio, an unevenly stretched ratio will optimize the experimental data. So we talked about how energy is applied in the theory and how the
Time's up.
rubber band has.
Okay, please come back. Okay, the reviewer, please ask your questions to everyone.
So we stabilize the launcher in a certain height and measure
The distance.
The distance.
I want to know on the floor. Where did you measure?
so where did you?
Like the middle where it landed or what?
The place when it lands.
Yeah. At one point or what?
Yeah, 1 point.
Okay. So did you consider the path offset? Like if you shoot in this direction, it flies to another direction?
So based on this splitting cause of matrix effect, you can exactly predict that it will be a certain trajectory. However,
Did you
vertical.
measure it? Did you measure
So we measure the distance, horizontal distance rather than.
So what do, as you mentioned the magnus effect, ideally what will it affect like if you shoot vertically and horizontally?
So ideally, the vertical shooting direction can cause a lift. However, because of the really small surface area of rubber band, this horizontally will cause a lift, slightly trajectory.
What do you think?
Well, I think that it certainly will function like a physics.
What does the turbulence affect? Like the distance or is it or not?
I think the turbulence will affect the vibration.
Can you consider it as an energy loss?
Yes.
I think the vibration actually might conserve some energy.
So when you stretch it unevenly, did you consider like will the K value change when you
Yes.
stretch it? And how did you consider it?
We apply the Young's modular equation in order to measure the change of elasticity throughout the stretching process.
Well, I think it is correct to assume that to use the Young's modulus in this case.
So for the same rubber band and the same for the same rubber band, is there a maximum distance in the same rubber band, like by changing the uneven stretching part?
Sorry, can you rephrase your question?
Is there a maximum distance in the same rubber band by changing the uneven stretching part?
Under the boundary condition we conduct, yes.
Okay. So did you know the ratio, like the ratio, like you stretch this side and this side?
I think that requires further calculation.
Okay. So did you measure like for the potential energy? We assume that it will change into the kinetic energy and the rotation energy. So right?
Yes.
And did you calculate the ratio, like how many changing to the kinetic energy?
Sorry, time's up. Okay, so you have 2 minutes to prepare. Reviewer. ready? Okay, yeah, go ahead.
Which the judges involved the computer side and the reviewer continue roles, and I'm going to review problem number 4 to remember. So this is the problem statement, and they focus on the relevant parameters and maximize the distance. So this is the overview of the reporter's presentation. For the observation and theory part, they used the Young's modulus equation and calculated the shooting velocity and the rotation velocity, and they calculated the energy loss, for example, the vibration and the unstable. And for their experiment method, they used a launcher and they calculated the elasticity of the rubber band, and they considered the energy loss, and they calculated the maximum of the rubber band of one rubber band can reach. And for the data analysis, they showed the experimental charts and the theoretical charts, and they used the Magnus. They said that the Magnus effect affects us very small due to the small contact area with the rubber band and the air. And the velocity and rotation velocity is shown like this. So these are the pros and cons. The pros is that they have a detailed theoretical model, and they consider the error changes in the formula, and they have diverse relevant parameters they consider. However, they can mention like comparing differences between the experimental and the theory. They have no error bars in some of their charts, and they have unfair definition on some of the formula elements, and they neglected the effect of spinning because they said that it's very small. And for the pros, the opponent brought up the idea of rotating, which should be important because the problem statement has said it, and they discussed the wave caused by the shooting. However, he doesn't really define what the wave he means, and the lack of suggestion like how to improve the experiment and to focus on the little factors in the formula. So these are the overview. They asked that will the release height change the trend of your experiment result, and the reporter's answer was no. And they asked that spinning isn't a main factor, and they said that the potential energy is a main factor, and the reviewer believes that spinning should affect the flight direction, so the offset during the flight should be measured. And they asked that where is the center of the mass of the rubber band, and they said that it doesn't matter, but the reviewer believes that since the shape is not stable, it will be hard to define, but if there is a torque that they are discussing, there should be a center of mass. And they asked that what caused the error bar, and they said that the different attack angle landing causes the vibration, and we think that besides vibrating, there could be air turbulence that affects the results. And so we asked them where did they measure the flight distance, and they say that 1 point of horizontal distance, and we think that they may, for suggestion, we think that they may tie the rubber band to mark the landing place, and like by measuring the middle part of the landing and add some error bars into the experiment data. And I asked that, did you consider the task offset? And the reporter's answer is that they do it horizontally. We think that due to the unevenly stretched, there should be a task offset, and it should be defined in the distance measurement. And I asked that, what is the difference between the vertically and horizontally shooting? And the reporter's answer is that the vertical causes a lift and the horizontal causes an offset, which the reviewer agreed with. And we asked that where does the turbulence affect the flight? And our the answer is that the stableness, like considered as an energy loss, and we think that it lessens the energy, and the more laminar the air is, the further it can fly. And I asked that will the K value change due to the uneven stretch, and they applied the Young's model to it. So we agree. For the next point, we think that they can focus more on the energy transferring and consider like different elasticity of the rubber bands, and also the K value change by the stretching result. And this is it. Thank you.
Okay. Yes, you can take 2 minutes.
So now I'm going to talk about the concluding remarks. First of all, the reviewer opponents might misunderstand our meaning about that spinning isn't the main causes of this longer distance. We do acknowledge the spinning's effects to this extension of distance. However, we believe that potential energy has a larger effects than spinning, and that doesn't mean we didn't think spinning is negligible. And we do consider the influence of rotational energy through integrating torque. And since the opponent didn't define the wave in depth, but we do include vibration in our experiment. However, there's still a possibility that this deformation the opponent mentioned is a possible deviation in our experiment. And for the Young's modulus to measure the elasticity of a rubber band throughout the motion. And I believe that the reviewer also talked about this offset distance that should be considered, and we acknowledge that this is some kind of thing that we can find to improve in our future research. And we thanks for the suggestions to both the reviewer and the opponent. Thank you.
Okay, now we have the 5 minutes for the questions from the jury. Next
How did you generate spin motion in your experiment, and how do you define the initial angular velocity of your rubber band?
I calculated the torque that created because of unevenly stretched and integrated with the unevenly stretched lengths that also corresponds to this angle of unevenly stretched length. And after integrated the torque with the angle, I get to the rotational energy. Therefore, I'm able to calculate it through divided by this moment of inertia and get to the angular velocity.
Okay. So do you for the three opponent again? Do you think the spin motion is the key point in this shooting rubber band experiment? Is the key point, key dynamics? I think yes.
As I just stated, that I acknowledge that spinning has an effect due to the it can lessen this vibration energy loss.
Okay. Opponent.
I think spinning definitely does affect, because although uneven stretching causes the potential energy to increase, it also causes the rotational energy to increase. So we need to deduct the rotational energy from potential energy to get the kinetic energy.
So to fly the furthest, I think it is necessary to like uneven stretching, because when it rotates, it actually stabilizes more, so it can make the rubber band fly further.
Did you know when you're shooting the bullet, the gun inside there are like 膛线. So why every gun, more expensive gun, have the line? Because when you launch the bullet can get an extra degree of freedom. That's rotation motion. So if when you play the top, total top, you play top and you just put on the floor, it's nothing but falling. But if you rotate the top, you can get an extra degree of freedom. That's nothing but rotation motion, and it can stable here. So I think, in my opinion, the rotation motion is very important point in this experiment. Okay.
So I do some kind of research about the point you just mentioned, but I think the difference between the bullet case and this rubber band case is that the rubber band actually doesn't consist that much of surface area, and that's why I consider this rotational energy.
So you see the surface, like frisbee and your rubber band, the key point you think is the surface. So you see you consider the air resistance. But I think the rotation motion is nothing is different from you say the magnetic effect. I think the extra degree of freedom is very important to stable your dynamics of the object.
I disagree with the reporter. Well, because if the surface area, the reporter thinks that the surface area is low, but the truth is the rubber band is also very light. So it might be easy to be subjugated by those kind of forces, which is like what you said, the degree of freedom, and it functions like a frisbee.
So did you do the experiment? The launch point is a little bit shifted. So the strength of the rubber band of two sides is different. I think you launch the rubber band on the center point, and you shift a little bit. So the length of the rubber band is different. So the stress tensor storage in the rubber band of the two sides is different. Do you do like this experiment?
Any questions? Oh, okay. You still have 50 minutes, 50 seconds. You want? Yeah.
So, using how to prove experimentally the spin is important or not. If you try to design an experiment.
So, as I just stated, that there's two ways to increase the initial velocity of the stretching rubber band. One is the original elongation length, and the other is the stretching length, unevenly stretched length. So there will be some cases that you have elongation length that's longer, but you didn't possess this unevenly stretched, and another sample with shorter elongation length that possess evenly stretched length that theoretically consist of the same velocity, and compare these two groups. And I think that's the way that test the spin.
Okay.
Well, I think you should
Maybe
measure.
shorter. Okay.
You should measure the angular velocity and discuss how energy is converted.
Reviewer, do you want to answer or no? No. Yes. Okay. Go ahead.
I think we should try different ratios of the pull distance for the both sides, and because there will be a ratio if you pull the two sides the same length of the two sides, there will be mostly transferred into the kinetic energy. Like it won't rotate too much, but it just goes far, and it's not stable. But if you extremely
Make it shorter, okay?
Can I use it quickly? Okay. If you use it really small length and a really large length, and it rotates more, so in our perspective, it transfers more into the rotational energy. So there must be a best ratio, like the rotational energy and the kinetic energy can form a most stable and most far distance of the rubber band.
Okay. Good. So you ready? Are you ready?
Yeah.
我在走迷宫，
So we have the score to the reporter. Okay, 6, 8, 7, 6, and 6. And the score for the opponent. 7, 6, 7, and 8. And the final one for the reviewer score. 7, 6, 6, and 7. Thank you. So we should come back in 10 minutes.